Okay, so there's a couple of things that an equilibrium constant allows us to do. First, it allows us to answer the question, is a system at equilibrium? Okay, and the way we can do that is by trying to figure out whether or not the system meets the requirements that the equilibrium has dictated, which is going to be given to us in our equilibrium constant. Okay, so let's say that we have a reaction. Again, we're going to keep this in real general terms, where we have some compound A, okay, reacting to produce some compound B, where we know the equilibrium constant. Okay, remember the equilibrium constant tells us where the position of the equilibrium is going to lie. So we can have a number that is much greater than 1, where we would have mostly products. We could have a number equal to 1, where we have kind of an equal mix of reactants and products, or we could have a value that's less than 1, where we have mostly products and very little reactants. Okay, so how do we do this? Well, what we do is, if we're given a system and we're told what the concentration of each one of the components is, we can calculate what's called the reaction quotient, okay, which is Q. Now here's one of the trickiest things in all of this discussion. Q is calculated exactly the same way as K. Okay, so whereas K is going to be equal to the concentration of B raised to the power of B divided by the concentration of A raised to the power of A, where both B and A are at equilibrium. Okay, the reaction quotient still uses the concentration of B raised to the power of B divided by the concentration of A raised to the power of A, but we don't know whether or not we're at equilibrium. Okay, so what we're going to do is we're going to calculate this reaction quotient given the amounts of reactants and products that are in the reaction. And we can wind up with one of 3 scenarios. The value of Q can either be greater than K, equal to K, or less than K. Okay. Now, if Q is equal to K, that means that these concentrations must be equilibrium concentrations. So if Q equals K, we are at equilibrium. And we don't expect that the reaction is going to proceed in either direction. Okay, if Q is greater than K, okay, that means that we have too much of the numerator, not enough of the denominator. In other words, we have too many products. Okay, the only way that we can have less products and more reactants is if the reaction is going to shift to the left. Okay, so another way of looking at it is that the reaction will shift towards the reactants, or shift to produce more reactants. And therefore consume some of the product. Okay, and if Q is less than K, that tells us that we don't have enough products yet, and therefore the reaction is going to shift to produce more product. Okay, so if we do this test, we can determine whether or not a reaction is at equilibrium, whether or not it's going to be moving towards the products, or if it's going to be moving towards the reactants. All right, so an example of a problem that would use this technique would be if we were looking at a reaction at equilibrium, or a reaction that is an equilibrium process, where we know the equilibrium constant. In this case, it's 6.5 times 10 to the fourth. And let's say that we are given the concentrations of all the reactants and the products. So let's say that we know, that was no pun there, the nitrogen oxide, or nitrogen monoxide, has a concentration equal to 1.0 times 10 to the negative second molar. That the chlorine has a concentration that is equal to, let's see here, 4.2 times 10 to the negative third molar, and that the nitrogen, let's see, the nitrosyl chloride, I believe it's called, this has a concentration of 3.4 times 10 to the negative third molar. Alright, now these are concentrations that we don't know would constitute equilibrium concentrations, so we're just going to call these initial concentrations. We don't know what they are. Okay, what we need to do is to figure out whether or not this reaction is at equilibrium. And the way that we do this is by calculating Q. Okay, the expression for Q is going to be exactly the same as the expression for K. So it's going to be the concentration of the products, which is NaCl, raised to its coefficient, which is 2, divided by the concentration of nitrogen monoxide raised to its coefficient, which is 2, times the concentration of chlorine raised to its coefficient, which is 1. Okay, so now all we have to do is feed these values into the equation. So we get 3.4 times 10 to the negative third squared, divided by nitrogen monoxide, which is, let's see, 1.0 times 10 to the negative second, and that'll be squared, times the concentration of chlorine, which was 4.2 times 10 to the negative third. Okay, and we put this in our calculator. Okay, and I get 27.5. Okay, so what does this mean? Well, Q is equal to 27.5. K is equal to 6,500. Actually, no, 65,000. Okay, so clearly Q is going to be less than K. And we said that when Q is less than K, there's not enough product there. So the reaction is going to have to proceed towards the right side. So the reaction is going to go from left to right, or go towards the products. Okay, and it's going to keep on doing so until Q equals K. Now the second question that we can answer with our knowledge of the equilibrium constant is, what will the concentrations be at equilibrium? So if we have a reaction that's known to achieve equilibrium, we know its equilibrium constant, and we know what the initial concentrations are, then we can predict what the equilibrium concentrations are going to be. Okay, so let's try an example here. Okay, so let's suppose that we are looking at a reaction like H2 plus iodine yielding 2 hydrogen iodides. Okay, and we're told explicitly that the initial concentration of the hydrogen is going to be, let's see here, 0.40 molar. I'm sorry, not 0.40, 0.040 molar. Okay, and we are told explicitly that we start off with nothing but HI, and that its initial concentration is 0.040 molar. Okay, and if we're starting off with only HI, that means that our concentration of H2 initially is going to be 0, as is our initial concentration of the iodine. Okay, now this is an equilibrium reaction, which means if we don't have any hydrogen or any iodine, the equilibrium is going to have to shift towards the hydrogen and the iodine, so go from right to left. Now, the way that we do this is by setting up what we call an ice table. Okay, in an ice table, we start off by writing out the equation. Okay, and then on the left side, oops, didn't mean to write that. We put I, which stands for initial, C, which stands for change, and E, which stands for at equilibrium. So we know the initial concentrations of everything here. So hydrogen 0, iodine 0, and the hydrogen iodide is 0.040. Okay, that's molar, but we'll just remember that. And we know that in the course of achieving equilibrium, okay, some amount of the some amount of H2 will have to be produced. Okay, we'll call that X. And because of the way the equation's balanced, for every mole of H2 that we produce, we're going to have to also produce a mole of iodine. Okay, so the concentrations are going to increase by a factor of X. And then for HI, we're going to lose some of that. Some of that's going to be converted to H2 and I2. So we're going to lose 2 times X, okay, because we're going to lose 2 HIs for every H2 and I2 that is produced. So that at equilibrium, we should have X molar H2, X molar I2, and 0.040 minus 2X of the HI. Now, we need to know what the equilibrium constant is for this reaction. Okay, and that equilibrium constant is 54.3, which, based on the equation, is going to be equal to the concentration of the products, which is HI raised to the power of 2, divided by the concentration of the reactants, which is H2 and I2. Okay, so now to calculate what the equilibrium concentrations are going to be, we just plug these values in. So we have 54.3 being equal to 0.040 minus 2x, and all that squared, divided by x times x. Okay, now we just have to solve for x here, so let's work our way through this. Okay, so I wind up with x being equal to 4.3 times 10 to the negative third. The way that I did this was taking the square root of both sides of the equation, and that allowed me to simplify things down considerably, did a little bit more algebra there. Now, x is not our answer. Okay, we know that our equilibrium concentration of H2 is going to be equal to x, which for that it's going to be 4.3 times 10 to the negative third molar. Okay, we know that iodine, its equilibrium concentration is going to be equal to x, which again is 4.3 times 10 to the negative third molar. Now Hi is going to be equal to 0.040 minus 2 times x, which is again 4.3 times 10 to the negative third. And for that, I get 0.0315 molar. Okay, so these are our final answers. These are the equilibrium concentrations that we would attain. Now you can imagine there's a couple of different ways a problem like this could be thrown at you. You could be given just some product to start off with. You could be given reactants to start off with. And sometimes you might be given products and reactants to start off with. And if both products and reactants are present, before you can even do this calculation, you need to do the Q calculation to figure out which way the reaction is going to go, which will tell us whether or not we are adding to the reactants and subtracting from the products, or are we adding to the products and subtracting from the reactants.